So this is the fourth and final video for week one. And in this video, we're going to be talking about how to construct a structural econometric model. We already talked about what they are, combining economic models with statistical assumptions to come up with an estimating equation that we can kind of estimate using these kind of structural estimation methods, which is going to be the whole topic for the rest of this course. But let's kind of give an outline for how to construct one of these structural econometric models. You're going to start with economic theory. It's going to depend on the economic setting, kind of primitives that you are wanting to estimate, what exogenous variables you have available to you, or which might depend on your data and your setting. What's the objective function? Are you thinking about consumers choosing quantities to maximize utility? Are you thinking about firms choosing input quantities to maximize profit? Or what else might you be thinking about? And then some kind of an equilibrium concept if you've got multiple sides of a market all going into your model. So we're going to start with that. This is obviously just a really quick, rough outline of how you would do this because it's going to be very context specific. So I'm not going to be able to tell you how to construct your structural model because that's going to depend on what you're trying to estimate. So once we've got that economic model, we're going to transform it into an econometric model by thinking about what unobservables make it such that the data aren't going to perfectly fit our model. Right, so it could be that we have uncertainty about the economic setting. It could be that the agents in the model have uncertainty about the setting. It could be that they have some optimization error. It could be that there's measurement error in our observed variables. There's probably a long list of things you could put in here, but there are lots of reasons why our model's not going to perfectly fit the data. But once we transform our economic model into an econometric model, then we can think about estimating it. We might have to make some functional form assumptions or some distributional assumptions if those didn't already happen in steps 1 and 2. Then we need to think about what kind of estimation methods are we going to use, and then kind of doing inference, things like specification tests. So let's see an example of this. This is going to be a simple example of a structural model. Let's say we want to estimate the output elasticities of capital and labor for a firm when we observe output, capital, and labor. Well, we can start with a Cobb-Douglas production function, right? There might be lots of production functions that fit, but economic theory tends to rely on a few that are kind of good for estimation purposes. So we're going to use a Cobb-Douglas production function, which we have here. Now, let me just use the cursor. Y equals A times K to the alpha times L to the beta, which we can then take the log of that and rewrite it as log of y equals gamma. We've just transformed log of A into gamma, plus alpha times the log of k, plus beta times the log of L. All right, so this is just kind of from economic theory. We know one possible production function is Cobb-Douglas, and this is what it looks like once we log it. All right, that's our economic model. Now we want to turn that into an econometric model. So we need to add an error term to capture, in this case, let's think about measurement error. And then we need to make some statistical assumptions about it. So let's just tack on an error term at the end here. We're going to assume that it's normal, distributed normal, mean 0, and variance sigma squared, and that error term is orthogonal to our capital or our labor. So those are the assumptions we're going to make. Do those seem reasonable? I would say no, but we're going to use them anyway, just to make this a simple and easy to illustrate example. This one in particular is the error term, is our measurement error orthogonal to capital and labor? In other words, are capital and labor being exogenously determined? Probably not, right? The firm is optimizing capital and labor, and it would not be surprising if something having to do with the optimization and the quantities there is correlated with some unobservable that maybe the firm knows about, but we don't know about, that there's something more than just measurement error going on here. But let's make that assumption just to keep this simple and easy. Then we've got this nice equation here. The log of y equals gamma plus alpha times the log of k plus beta times the log of L plus an error term, which we have defined such that we can estimate this equation using OLS. The alpha and the beta are going to be those output elasticities that we want. So we have just constructed an example here where we've got a kind of simple structural model. Some people might not even call this a structural model because we're just estimating one firm. We're not even estimating a whole market, but we've got this economic theory of production at least, and we're estimating parameters of that production function. And we can do that using OLS in this case. A lot of times, though, you're not going to be in a setting where you can just simplify your structural model down to an OLS equation. So let's look at that. Let's go back to auctions. Auctions are a great place to think about structural methods because there's so much theory already and kind of so many interesting things that we might be able to think about. So let's suppose that we observe the winning bid, which we're going to call W, from capital T different procurement auctions, each of those having capital N risk-neutral bidders. And we want to estimate the underlying common distribution of costs, which we're going to call F of C, known to all bidders. So every bidder has a cost, C, that's being drawn from some common distribution. Those bidders are going to come together into an auction. They're going to bid, and then the lowest bid wins with winning bid W. We see W, we see the number of bidders, and we want to reconstruct what the underlying common distribution of costs must be. Try to think about a way to do this using non-structural methods. We don't even observe anyone's cost. All we observe is winning bids. But we're going to be able to come up with the common distribution of costs. Think about trying to do that in a non-structural way, though. But here's one way we can do it in a structural way. So we're going to start with theory, right? Economic theory tells us, let's assume that firms are profit maximizing. Then they're going to maximize their expected profit, which is given by this formula here. I don't want to get too bogged down in the math and like the auction theory that's going on here, but the basic idea is if you win, then you're going to get whatever your bid is, but it's going to cost you whatever your cost is. So you're bidding above your cost, you're going to get B minus C. But that's going to come with some probability. What's the probability that you're actually the winner? And you want to maximize that expectation. We can differentiate that profit function to get a first order condition, and we're going to come up with this function here that firm I's bid, which we're going to call beta. We're going to construct this beta function, which is a function of cost. So a firm's bid is going to be a function of its cost plus all of this going on here. And like I said, I don't want to get into the auction theory. There's a lot of math that gets you from this line to this line, but this is still just under the assumptions in our theory we're getting here. We can also know that the distribution of winning bids then is going to look like this final equation here. So we've gone from expected profit maximization to a distribution of winning bids. That's all coming from the theory. Now let's assume that distribution of costs that we want to estimate comes from a family of distributions parameterized by theta. There could be some number of parameters there. Maybe we're going to assume it's normal. We're not even going to make an assumption on the shape yet. We're just going to leave this as general as possible, but there's going to be some set of parameters that can pin down what our distribution of costs look like. When we make that assumption, the lower bound of the distribution of winning bids is going to be this J term here, which is going to be a function of our parameters and the number of participants in the auction. This is what the lower bound is going to be. We basically just got that by plugging in C equals 0 in one of the previous equations. All right, so now we know the distribution of winning bids, and we actually observe data on winning bids. We know what the minimum, the lower bound of winning bids should be as a function of the number of participants, and we know how many participants there are. And both of these things depend on these theta parameters. So we can use maximum likelihood. This will make a lot more sense in a few weeks when we've talked about maximum likelihood, but ultimately we can use maximum likelihood to try to find what set of theta parameters basically make our data match that distribution from the previous slide and also don't violate this lower bound constraint that we just constructed here. So we're going to figure out what set of parameters make it most likely, kind of bring our data and our model as closely in alignment as possible without violating this constraint that we just constructed. So you can tell that that's definitely something we couldn't do with just a simple OLS model. There's a lot more going on here, a lot more reliance on theory, a lot more reliance on making some statistical assumptions, and then ultimately a totally different estimation method. So just to kind of summarize, I think these two models, I hope they nicely illustrated the point that some structural models can be estimated using OLS or some other related kind of simple regression that's going to be easy and fast to implement. It's going to be an estimation procedure that's transparent with underlying assumptions that are transparent. We pretty quickly picked up on the fact with that OLS structural model that we might be making some unrealistic assumptions about the exogeneity of K and L. And then the results are easily interpreted because everyone's familiar with OLS regressions, and if you show them some results, they know what those mean. But then, of course, some structural models require more advanced estimation methods. They can't be simplified down to a linear regression model. Instead, we're going to have to get ourselves to a log likelihood function or conditional moments or something like that we're going to use these other methods to estimate. And I'm going to kind of broadly define those as structural estimation. And what this course is going to focus on are those kind of other structural estimation methods that follow from this second class of structural models. Things like maximum likelihood, generalized method of moments, their simulation-based counterparts. So to bring this around, this course, if we want to kind of put this course into that three-step framework that we've talked about in this video, we're going to start with an economic model of discrete choice where agents are trying to maximize their utility. We're going to turn that into an econometric model using the random utility model, making some different statistical assumptions. This is going to get us to three different discrete choice models: the logit model, the nested logit model, and the mixed logit or random coefficients logit model. Those are going to be kind of the three main kind of structural econometric models that we use in this class, just so we can kind of keep a consistent framework. And then to estimate those models, we're going to use these structural estimation methods: maximum likelihood, generalized method of moments, maximum simulated likelihood, and method of simulated moments. So that's the last slide that I have. I hope this whole series of 4 videos here for this week have given you at least kind of a flavor of what we mean by structural models and structural estimation. I don't expect it to have fully sunk in, but I hope you can see that we're going to be doing something very different from what you've done in kind of OLS classes, based classes in the past. And it's going to kind of open you up to new types of econometrics that you can do, and new kinds of parameters that you can estimate, and just kind of an entirely new framework for thinking about estimating economic models. So I'll stop there for this week. Next week, we're going to be talking about R. So be on the lookout for those videos.